Okay, so when we're talking about segment relationships, we have, or within a circle, we of course need to have a circle. Let's draw one of those. Here's our circle. And there are 5 different types of lines. So we're going to start with the most basic type. And that is when we have a chord that intersects another chord. Okay, so our first segment relationship is going to be a chord-chord relationship. Okay, what happens when a chord intersects a chord? So let's draw that in here. Let's get a line. So here's one chord, and here is a second chord that, of course, intersect. So they cross. Okay, and when they cross, they create 4 different segments. We'll call those segments A, B, C, and D in no particular order. Okay, so there is in fact a relationship between them, and let's see if I can do another thing so that we can figure out what that relationship is. So here I have a circle. There's my circle, super duper. Let's move it down here. And here we had a chord, correct? From circle to circle, and there's another chord right there. Okay, so this intersects, and they have 4 different lengths. So we have from the edge to the intersection. We have from the intersection to the other edge. Ooh, that's let's start over. All of that. Delete. Anyway, as I was, make a circle. Come here, circle. A great recording live. There we go. Here we go. There, let's make it a little bit bigger and move it back to the middle. Okay. So once again, we have 4 segments. This one we called B, I believe. This one we called A. This one we called C a second ago, and this one we called D. So that was A here, and B here, and C there, and D here. So it turns out that if I measure all these things, see if I can measure all of them individually. Measure lengths. Okay, notice there's not a whole lot going on. I can move these around, and there's no real relationship between the lengths yet until I start multiplying them. So it turns out that these things chop each other proportionally. Proportionally. So if I take the segment from A, which is this one, and I need to do some calculating. If I take this length and I multiply it by the other part, which was AC, right? So that's this length times that length. And if I do another calculation and multiply it by the other 2, looky what happens. Nothing whatsoever. And that is because this is the wrong measurement. Delete you. Let's see if I can get it right. There we go. Let's measure this one. See, recording live is lots of fun. So where was I? Here I was. I was calculating this times this. That looks much better. So no matter how long they are, when I bisect them, or not bisect, but rather intersect them, if I were to multiply down each chord, okay, this part with that part and this part with that part, they come out to be the same thing. So that's one of our properties when I have a chord multiplied by a chord. This length times that length, so A times B, continuing down, this segment of my chord times that segment is equal to the product of the other two. Okay, this portion times that portion. Okay, hopefully this sketch over here illustrated that, even though it took me a while to get it right. But when I multiply the segments, when the two chords intersect, you always get the same product. So that's how the chord-chord relationship works. Okay, so we have some other ones. Where's my circle go? Here's my circle. Oops, there we are. Okay, what happens when a secant and a secant get together? So here is one secant line, like that. And here's another secant line right here. So we once again have a couple portions. We have an inside portion and an outside portion, and an inside portion and an outside portion. Okay, and what we find when we have a secant and a secant, so this is a secant and a secant that meet together, is we get the entire length. If we take the entire length and multiply it by the outside of one secant, that will be the same thing as if we do it over there. Okay, it's equal to this entire length times its outside. So if I were going to do that mathematically, that would be A plus B, the entire length of this top secant, times the outside, which is just B, okay, the part outside of the circle. That equals the entire length of the other secant, okay, C plus D, times its outside length. Okay, so the entire thing times the outside is equal to the entire thing times the outside. Let's go over here to our sketch and see if we can't verify that with a new sketch. So I had myself a circle. Bring it back in here. Come here, circle. And I had two secants. So I had from here to the outside, and then it had to have the same endpoint, and like that. Okay, so one thing was the entire length. So let me measure these entire lengths. Select, select. Measure entire length. So this is the entire length of that top secant, and this one is the entire length of the bottom secant. Now the other part I had was the outside. So let's see, intersect our circle, come to the outside, intersect our circle right there. I think this one was suspect. Let me delete him. And that point, get out of here, point. Let me draw it the other way. So from my point here where it intersects. There we go. So it's important when we're doing these programs to actually get it in the right spot, or it won't work out mathematically. So let's measure these two lengths. Length, length. There we go. All right, so it looks like BD is the top one, right? There's the outside there. And BE is the outside one from the bottom chord. So let's do another calculation. Sorry. The entire length times the outside. No, I want you to go up here. And another calculation to see the entire length, which was BC, sorry, times the outside, which is in this case 8.44. And you see, no matter how long my secants happen to be, 67.85, 67.85, the product of the entire length times the outside is always the same as the entire length times the outside. Okay, so we can verify, by no means is this a proof, but we can verify that the relationship exists, that those things are in fact good to go. So when we have a secant-secant, you take the entire length and you multiply it by the outside length, and that equals the entire length times the outside length. Okay, here's another one. So let me get another circle. Circle, circle, here's my circle. Okay, and this one happens when I have a secant line and a tangent line. So this is a secant and a tangent. So let me draw a secant. There's my secant. And then the tangent is a line that touches exactly one spot. Let's say right there. Okay, so our secant one is the one that goes through your circle, and the tangent is the one that touches your circle. So once again, we have three lengths. We have an inside length, we have an outside length, and we have the tangent, which I'm just going to label T or tangent. Okay, very similar to secant-secant, but when we come outside of it, so we have the entire length of the secant times the outside equals, for the tangent, the entire length and the outside are the same. So tangent squared. Multiply it by itself. So that looks like A plus B times B, the entire length times the outside, equals the tangent squared. That's the relationship there. Now let's see. Let me get a new one and see if we can verify this. So we need a circle. Okay, the important part is to make the tangent line, and the tangent line has to be perpendicular. So I'm going to start off with my tangent. So I'm going to make something perpendicular to this. So I'm going to construct a perpendicular line. There I go. Move it down here. So now I'm going to draw a secant, which is going to go from down here to over there. So there's where it intersects. And then let's just bring it down to here. So this is my tangent line. This is my secant line. Okay, no matter where it goes, it will always stay tangent, and it will always be secant, no matter what. So let's measure some lengths. Let me measure my secant. Measure length. There we go. Move down over here. Measure my tangent. There it is. Measure length. Let's put it up here. And now I need to measure the outside part. So from here to there. No, it didn't touch it, did it? See if I can move it so it does touch. Nope. Delete. And try again. I need it to be the intersection point exactly. There we go. Measure that length. So let's move it down here where it goes. So the relationship was the entire length, which is this one, times the outside portion, which was that. Okay, so there's that product. needs to equal number, calculate this thing raised to the second power, or that thing squared. So we can verify by moving our things around. I will move my tangent. Oh, that's the whole thing. I'll move my tangent line. And you see the product, well, in this case, is always constant, no matter where my things go. Okay, so the product of the outside times the entire length for your secant is equal to the product of the tangent. And in fact, it's always constant, no matter where your tangent line happens to be. Let's see if I can make this change. Oh, here we go. I'll make this smaller. There we go. And you can see that the product is still the same, no matter what happens. There, verified but not proven. So those are your segment relationships. We have a secant-tangent relationship, we have a secant-secant relationship, and we have a chord-chord relationship.